Hi everybody, in this video we're going to demonstrate how to use pre-trained semantic segmentation models that are hosted on TensorFlow Hub. TensorFlow Hub is a central repository for sharing and reusing a variety of pre-trained machine learning models provided by Google. TensorFlow Hub contains many other types of models, but the focus of this video is going to be on how to use pre-trained segmentation models to perform inference on some sample images. If you're not already familiar with semantic segmentation, we do have an introductory post on the topic, which we've linked to in the description below. In this notebook, we're going to use a specific pre-trained segmentation model that was trained on the CamVid dataset, which is a dataset that contains images extracted from videos of common driving scenes. But before we get started with the coding implementation, let's just take a quick look at the TensorFlow Hub site. Here we've provided a link to the image segmentation models on the site, but notice that in the upper left-hand corner there's filters that you can set to look for a wide range of different models. And in this case, since we're on the image segmentation page, you can see all the different segmentation models that are available. And so let's go ahead and navigate to the HRNet CamVid model that we're going to use for this example. If you click on any one of these models, it'll take you to a model-specific page in which you can copy the URL to the page, download the model, or even open the model in a Colab notebook. And then if you scroll down a bit further, there's usually a little bit of code that provides an example use case. So that's just a quick summary of what the site looks like and how you access the models. And let's go back to the notebook now, and we'll continue on with the coding implementation of how to use such models. So we're going to start by downloading some sample images from the CamVid dataset to experiment with in this notebook. So after we've downloaded and extracted the archive, we're going to use the glop utility to build a list of image paths. And just for confirmation, we're printing out those paths to the console as shown here. In this next code cell, we're going to define a convenience function that takes a single image path as the argument and reads the image into a NumPy array. And notice that we're also adding a batch dimension to each of the images, and we're also normalizing the images by dividing by 255. And the reason that we know to perform these operations is because on the documentation page for this model in TensorFlow Hub, the sample code provides an explanation of this. So that's not always the case. So depending on what type of model you're using, you'll want to take a look at the documentation in TensorFlow Hub to understand how the images should be pre-processed. So next, we're going to use that convenience function to load each of the images into memory and display them to the console. Each of these images from the CamVid dataset were taken from individual frames within a video sequence from a car-mounted camera. And you can see that these are very natural, common images that you might expect from a car-mounted camera, full of lots of clutter, but also things that you might be interested in segmenting. For example, the road, people, cars, sidewalks, those types of things. And it turns out that this particular data set actually has 32 different classes in it. And so it'll be really interesting to see how the model performs on images like this. So one of the things that we're going to need to formalize here so that we can interpret the results correctly from the model is to create a mapping from class IDs to class names, and also RGB color values for each of those classes, which is going to help us visualize the results in the form of a segmentation mask, also sometimes referred to as a segmentation map. So we'll make use of this dictionary further below in the notebook. So now we're ready to talk about how to use the model, and the first thing we need to do is load the model into memory, which is a very straightforward process. All you need is the model URL, which is indicated here, and you use the TensorFlow Hub load method to load the model, providing the URL, and that returns for you an instance of a model that's in memory. And so let's go ahead and scroll down to the next section then and see how to use that model. Before we formalize the process for using the model to perform segmentation on a set of images, we're going to start with just a single image so that we can walk through all the steps that are required to interpret the results from the model. So in this first code cell here, using the model's predict method and passing in the first image from the list of images that we read in earlier. So we're going to process just one image, and this returns for us a predicted segmentation mask. And notice that the dimensions of that mask are the batch size, the spatial dimensions of the mask, which are the same dimensions as the input image, and then the last dimension represents the 32 classes in the data set, plus a background class that's added by the model. And you can think of the background class as being associated with regions of the image that don't belong to any of the other classes in the data set. So each of the channels in this segmentation mask represent a specific class, and the entries in each of those channels represent the probability that a given pixel at that location is associated with that class. So this predicted segmentation mask, you can think of it as a raw prediction data, which needs to be post-processed in order to correctly interpret the results. So there's several steps that we need to go through, and it'll be useful to just walk through those one step at a time so that we can understand the process and what's contained in these masks, so that we can then formalize that a little bit later in the notebook to process all the images in one fell swoop. So in this next code cell, there's a couple of things that we're going to do right off the bat. First, we're going to convert the predicted segmentation mask from a tensor to a NumPy array. And then following that, we're going to remove the background class from the predicted segmentation mask that was added by the model. And then finally, we're going to remove the batch dimension, which is not needed for post-processing the predicted segmentation mask. So after those processing steps, you can see that the predicted segmentation mask now has a shape of 720 by 960 by 32, where the 32 represents the 32 different classes in the CamVid dataset, where each of those channels contains the probabilities associated with a particular class for any given pixel location. So before we continue on, we just wanted to make a few comments regarding this background class that was added by the model. If you take a look at the documentation for the model in TensorFlow Hub, you'll notice that there's a comment there in the example use case that indicates that the model is adding a background class. And notice that the comment has a typo. It should say 32 plus 1, not 23 plus 1. But this isn't necessarily required, since we have 32 classes that pretty much encompass all the different things that we'd expect to see in these images. It doesn't hurt to add a background class in this case, but for this data set, the effects of adding one are going to be negligible, and in the interest of maintaining the original class IDs, we've decided to remove it. And just as a side note, you might notice that the data set has a void class, which is similar but also different from a background class. The void class is used to label regions in an image where the true class is uncertain or unknown or ambiguous, and therefore these regions are typically ignored during the evaluation of the model's performance, since the ground truth for those regions is not reliable. A background class, on the other hand, is an actual class that the segmentation model is expected to recognize and classify. But again, for this data set, a background class is not really required and will make little, if any, difference in the results. So let's now continue on and try to get a better understanding by taking a look at some of the data. In this next code cell, we're displaying the original input image on the left, and then two specific channels from the predicted segmentation mask. So in this case, we're showing the segmentation mask for channel 17, which is associated with the road, and channel 21, which is associated with the sky. So the data in each of those channels is the probability for that class for any given pixel location. So all the pixel values for any given channel are going to range between the values of 0 and 1 because they're probabilities. We can also display that data as a grayscale image, and values that are close to 0 are going to appear black, and any values that are much greater than 0 will look light gray or white. And the fact that these values only range between 0 and 1 is not a problem, because Matplotlib will just scale these accordingly. So it'll essentially normalize the values so that the minimum value in the image is black and the maximum value in the image is white. And so what we're seeing here is that the model has done a very nice job of identifying the road and also identifying the sky in those two channels. And so now that we have an understanding of what's contained in each of those channels, the next few steps will make a lot more sense, where we're going to assign a specific class to every pixel location, considering all 32 channels. And the way that we're going to do that is we're going to select the class for every pixel location that has the maximum probability across all 32 classes. So you can think of that process as collapsing all 32 channels into a single channel that represents the final segmentation mask, where each entry in that mask is the class associated with the maximum probability across all 32 classes. And so we'll see how that operation is performed with just a single line of code in the next section below. So here we're calling the argmax function, passing in the predicted segmentation mask, and recall that this mask has 32 channels that contain the probabilities for each class. And this function will return for us the index associated with the channel that has the maximum probability. And so the result is a single channel representation of the segmentation mask that contains the class IDs for those classes that had the highest probability for their given pixel location. So the entries in this mask are now the integers 1 through 32, representing the 32 different classes, which we can conveniently view as a grayscale image to isolate each of the classes. And notice that we've also annotated the image with a thin horizontal red rectangle near the middle, and we're going to zoom into that area in the next section below to inspect some of the data inside the segmentation mask. In this next image, we've displayed the top portion of the segmentation mask overlaid on top of the original image, and we've also annotated the image with the class IDs associated with each region in the image. So as you can see, the darker values to the left are associated with buildings, which are class ID 4. The center of the image, which is the sky, is associated with class ID 21, and then the trees to the right are associated with class ID 26. And then you'll notice also that there's a couple of regions associated with signs on the building, and those are class ID 12. But let's just focus on the thin red rectangle at the bottom of the image frame. Here we've identified one row of the segmentation mask. And in the next section below, we're going to print out the values of that portion of the segmentation mask. So let's take a look at that. Here you can see that we've printed out 200 values from that portion of the mask, consisting of class IDs 4, 21, and 26, moving from left to right, which consists of the buildings, the sky, and the trees. So we're almost at the point where we can visualize this in a way that it will be very obvious which classes are which. So all we need to do is turn this into something more interpretable, which is would be an RGB color image, and we could use a color legend to determine which class is which. So the final step then in this process is to convert the grayscale segmentation mask into a color segmentation mask. And here we have one more convenience function called class to RGB, which takes two required arguments, which are the grayscale segmentation mask and then the class index dictionary that maps class IDs to class names and also RGB color values. So the first thing that we do is create 3 separate RGB channels that are the same size as the segmentation mask, and then we're going to use the class index dictionary to map class IDs in the segmentation map to RGB color values for the color segmentation map. And then we just stack those RGB channels together to create a color segmentation map, which is returned as segmap RGB. And then in the following code cell, we use that function, passing in the grayscale version of the segmentation map, which contains class IDs, along with the class index dictionary. And that returns for us a color segmentation map. So here we're showing the original input image on the left, the grayscale segmentation map in the center, and the color segmentation map at the far right. And so you can see that the color segmentation map is much more interpretable than the grayscale version, which is why this is the standard representation for segmentation results. So now that we've taken the time to walk through the individual steps required to post-process the results from the segmentation model, and we have a good understanding of how those results are achieved, we're going to formalize the implementation a bit further in the last section of the notebook, and for that purpose, we're going to create a few more convenience functions that further consolidate all these operations so that we can process multiple images at once with just a few lines of code. So let's go ahead and take a look at that next. So this first function that we have here called image overlay will be used to overlay the color segmentation map on top of the original image with some transparency factor so that you can still see the original image beneath the segmentation map. And this is useful so that you can get a better sense for what the ground truth is versus what the model is predicting. So next, let's continue on and take a look at the main function called run inference, which is going to implement all of the logic to make predictions from the model and post-process and display the results. The function takes two required arguments, which are a list of images and a reference to the model, and then loops over each of the images. So the first thing we do is call the model's predict method, passing in the input image, and that returns for us a predicted segmentation map with 33 channels. I recall that there is a background channel that is added by the model, and then this is converted to a NumPy array also on the same line. And then the next line of code removes the background class because it's not needed, and then the following line of code removes the batch dimension. So now we have a segmentation mask that has the same spatial dimensions as the input image with 32 channels, where each channel contains the probability scores for each class. So we then need to pass this through the argmax function to assign a specific class to every pixel location in the map. And then the final step is to convert that single channel segmentation mask, which contains the class IDs, into an RGB color representation based on the colors that are contained in the class index dictionary that we defined earlier in the notebook. And that's all the processing that's required. So the rest of the code in here is simply a plotting code, which is going to display the original image, the predicted color segmentation mask, and then finally the color segmentation mask overlaid on the original image. And that last bit of code there uses the image overlay function that we just covered above. Before we execute this main function to perform inference on the sample images, we're going to define one additional function that will generate a color legend for us so we can use it to study the results. And this function takes one required argument, which is the class index dictionary, and extracts both the colors and the class labels from the dictionary to produce the legend below. And so this now acts as a nice reference for us to help us interpret the color segmentation masks. So now we're in a position to call the run inference function, passing in the list of images and a reference to the model. And you can see the results for the first two sample images below. And notice how helpful it is to have the semi-transparent segmentation mask overlaid on the original image. This way you can see what the original content was in the image and how those segmentation results overlay on the ground truth. So, for example, you can see in the very first image that the road is very well identified along with the lane markings on the road. The sidewalks are fairly well segmented, although there are some patches that are not quite right. And then notice also in the center of the image, there's two cyclists in the middle of the road, and the model has determined that those are a combination of a cyclist class and also a pedestrian, which kind of makes sense that that would be the case. And if we scroll down a bit further to take a look at the next set of results, in particular, I would point out just how well the road, the lane markings, and the sidewalks are segmented in both of these cases. And although we don't have time to go into it in this video, there are metrics that are commonly used to quantify how well the model has performed the task. So we hope that gives you a good feel for the processing involved with segmentation models, and especially how easy it is to use a pre-trained model from TensorFlow Hub. Keep in mind that there are numerous models available on the site for you to experiment with, and you could use this notebook to load other models and try them out. So we hope you found this video helpful. Thanks so much, and we'll see you next time.